Hello. We are going to work through 3 examples here in the second video for Unit 16 on simple machines. I guess I should be up here one slide more. The first set of examples we're going to work with, because there's multiple for this one, is thinking about levers. Okay, so think about a lever. What is a lever? I need my pen again. Here we are. Here's my pen. Okay, so we'll call this option A or example A. So let's say we have a lever and we put the fulcrum of that lever exactly in the middle. And then for ease, we're going to let the distance from the fulcrum to either end of the lever be 1 meter. Okay, now it's nice and centered. Makes it easy to think about. And for all of our examples, we're going to assume that whatever we're trying to lift is on this end. So I'm going to refer to this as the object end. And this end is where you're going to be applying the force. So I'm going to put you or us or however you want to think about it on that end. Okay, so the idea here is that you are going to apply a force downward, which is going to apply or cause the object to move upward. And I guess I shouldn't write that as F upward. So let's erase that and fix it. Again, so you're going to apply a force upward, which is going to cause the object to move up. Right? So this end of the lever will move down, this end of the lever will move up. And the amount it moves, if we think about now this lovely lever where it's been tilted, I'm going to draw a slightly bigger fulcrum. Horizontally, it was here. This end has now moved up that much. And this end has moved down this much. And notice that these two angles are equal. Okay? So, as we saw in the last video, the ideal mechanical advantage is going to be the ratio of how much the input side moves divided by how much the output side moves. Okay. Well, in the notation we have in our diagram there, the input side is going to be our D down, and our output side is going to be our distance upward. Okay. But how does that relate to the two lengths from the fulcrum? Okay. Well, we have 2 triangles, and they're identical triangles. One's just oriented the other way than the other. This is theta. This side here is going to be, our 1 meter. And this side here is going to be our distance upward. Okay. And so the distance upward is on the side opposite of our hypotenuse, which we know is 1 meter long because it's just our lever tilted. And that has to equal the sine of theta, the definition, SOHCAHTOA. So we can redo this, that the distance up will be 1 meter times the sine of theta. And we can apply that down here. And similarly, on the downside, remember similar triangles, I hope it's not a huge surprise that this is going to also be 1 meter sine of theta. So this gives us an ideal mechanical advantage of 1, which is unitless again. Okay. That kind of, I think, should be expected. Now let's look at a variation on this. Okay, and let's offset our fulcrum. So still a 2 meter long lever, but now I'm going to put the fulcrum over here so that this distance is 1/2 meter and this distance is 1.5 meters. Okay, well, just as we saw before, we can have the ideal mechanical advantage will be the, make sure I write it right, D down divided by D up. And remember, D down is the side that is going to be pushed downward. And D up is the side that, I'll write it down here, this side's going to move down, this side's going to move up. So this is going to be 1.5 meters. And I just wrote it wrong. Take 2. Can I just erase? Nope. Okay. Take 2. Erase it. D down is 1/2 meter, 0.5 meters, divided by our 1.5 meters, which that fraction is 0.33, right? So we're going to push down on the one side. The other side's going to go up. Where's the trade-off here? Well, it's in the forces, right? We're not really thinking about the forces. If our distance from fulcrum is different on the two sides, then the amount of force to get this to happen is going to be different. And you can unravel that because remember that you can relate the ideal mechanical advantage both to the amount that is moved and also to the forces. Okay, so a similar example, but now we're going to move the fulcrum to the other end. So this is going to be our 0.5 meters, and this side is going to be our 1.5 meters. And again, this is our downside, this is our upside, so our ideal mechanical advantage in this case is going to be what I tried to write for the last one and screwed it up. So it's going to be the 1.5 meters divided by 0.5 meters, which is 3. Yay! Okay. Now, the last example is what if our lever isn't straight? And I did this because I saw in the Hecht Schom's outline, one of the examples had a lever like this. Okay, so what if our lever looks like this? And I'm going to go back, even though it's not drawn that way very well, that both ends of the lever are 1 meter. But this guy is, say, up at an angle of 30 degrees, and I know that I didn't draw it really realistically for 30 degrees, but it worked for me. So there you go. Okay, so now the question is, what happens? Well, I'm still going to push this end down. This end's still going to go up. And they're still going to move similarly. But we got a small problem because this one's at an angle. So what am I going to do? Well, I'm going to redraw this lever. Leave that there. Going to make this 1 meter. And I'm going to call this a D effective. It's the effective length of that side of the lever. And we can find that effective length by, again, drawing a triangle. I'll draw it over here. I was debating. Here's our 1 meter. Here's our 30. I drew it as a theta. I'll pretend the theta is a 0. Here's our 30-degree angle. And our D effective is this side of this right triangle. And now we can see D effective is on the side adjacent. So cosine of 30 is the adjacent side divided by the hypotenuse. So if we unwrap this, D effective will be 1 meter cosine of 30, which is 0.866. And now the ideal mechanical advantage is going to take the effective length of what is moving down divided by the side that is moving up. So that's going to be our 0.866 divided by 1 meter. And that works out to being 0.866. Okay, so now why? Why is the ideal mechanical advantage here less than 1? Because our 1 meter length here as an angle, when we apply our force, the distance from the fulcrum isn't 1 meter. It's a fraction of that. That's why we take an effective length. Using our trig, we were able to find that effective length, and that gives us our ideal mechanical advantage for that situation. Okay. The next one, I have a blank slide. The next example we're going to work with is a screw. So we're going to have a screw here. I'm going to let the radius of the cap of the screw here be 0.5 meters. And then we got the body of the screw with all of its lovely threads to within my ability to draw this. This is what you get. Okay, so remember our ideal mechanical advantage can be viewed as two distances. The distance that you have to move versus the distance of the outcome. Okay, so in this case, what am I doing? Well, I'm rotating the screw head. So the distance in that I'm putting in is how much am I rotating the screw head. And then the output is going to be how far does that screw move down? Okay, so let's take the easier one first. So the distance of rotation, so the numerator of our thing up there, is just going to be the circumference of the screw. So this is circumference, which is just 2 pi r, which in our case is 2 pi times 0.5. And I wrote meters up here. Guys, a 0.5 meter screw head is ridiculous to think about. So let's make it centimeters, please. Right? Okay, we grab our trusty calculators, and 2 times pi times 0.5 is not needed to be done on a calculator. It's just pi, 3.14 centimeters. So in one rotation of the screw head, it goes around 3.14 centimeters. Okay, second part of this. The distance the screw moves down. Okay, that is related to the screw's pitch. And the pitch is determined by a distance divided by a number of threads. So let's say up here that I'm looking at a distance here. Let's let that be a centimeter. And if we count now my lovely scribbles, I have 1, 2, 3, 4, 5, 6. So if I count that as 0, 1, 2, 3, 4, 5, 6, right? So my distance here is going to be, nope, wrong thing. I have 1 centimeter of distance on my screw, and in that centimeters, I have 6 threads. So my pitch is going to be 1/6, which is 0.167 centimeters. Okay, And now we can go back and think about the ideal mechanical advantage as being the input distance divided by the output distance. Our input distance was the circumference of the screw head, 3.14 centimeters, because I'm moving one rotation. And in that one rotation, I will move down a distance equal to the pitch, which in this case was 0.167 centimeters. So I'm going to take 3.14 and divide it by 0.167, and I get an ideal mechanical advantage of 18.8. Okay. Lastly, we're going to look at pulleys. Okay, we're going to look at 3 variations of the pulley, but the 4th one we're going to use a simplification to do because it's going to get very complicated otherwise. Okay, so the first pulley is just going to be your very, very, very basic pulley. You're going to pull down on this side and lift a load on that side. Okay, if we think about this pulley, no, I don't want to think about the pulley. I want to think about what's going on with the tension in the rope here. Okay? And we have to make some assumptions. One assumption is that the string or the rope or whatever you want to think about attached to this pulley here, we want to assume it can't stretch. Okay? The second simplification that we're going to do is the pulley itself has no mass, or you could think about it as the mass of the pulley is negligible to the system. The load is much, much heavier than the pulley is. And then the last assumption we're going to make is there's no friction. Okay? That one had to be made in order for the ideal and mechanical advantage calculation. The other 2 are not as obvious, but are also necessary. Okay? Okay, so in this situation, right, and I think about the load here, it's going to have a tension upward, and it's going to have the gravitational force acting upward. But what's causing this tension? Well, with all of these assumptions, the tension is being caused by you. You're pulling on that rope. Okay? So the ideal mechanical advantage is the force of the load divided by the force that you apply. Remember, that's the definition of mechanical advantage in this case. And in these ideal situations, then the load is just going to be mg, and the force you apply will be this. And most likely, those are going to be 1 to 1, in which case your ideal mechanical advantage is going to be 1. Okay. So now let's look at a slightly more complex pulley system. Okay. In this case, we're going to take and run a rope around the pulley like this. So this is you. You're going to be pulling up. Okay. And the pulley is supported by a combination of the string attached to whatever ceiling or whatever's here, and whatever you're doing to hold it up. Attached to the center of the pulley is going to be the load. Okay? And the same simplifying assumptions have to hold. If I look at the pulley and look at its free body diagram, I have a tension upward. You're on the other end of that string, so that will eventually become you. We can even just label it here. But it's the same string, and there's another side to it. So I have 2 of those upward. And I also have on it a third tension, but that third tension is attached to the load. So this is going to be the load here, which is just going to be mg. Okay, now we're again going to make an assumption, and that assumption is that we're pulling up nice and evenly constant speed, in which case the net force on this pulley will equal 0. And we get 2 times tension 1 minus mg equals 0, or tension 1 equals, I'm doing my math backwards, mg divided by 2, which means that the force you apply is mg divided by 2. Now you're only lifting half of the load's weight. The other half is being lifted by the other side of the string, right? Okay, so now if we think about our mechanical advantage, it is the load force divided by the force you apply. So that's going to be mg divided by 2, which is 2. That's fantastic. Okay. Now, again, think about what happens with the distances, though, because I'm going to pull up here, and this is only going to move half as far as I pull up, because the distance is going to be divided between the two sides of the string. Okay, so it's a trade-off. I have to apply a smaller force, but it doesn't move as far. Okay, now notice this number 2. And notice up here that we have 1, 2 ropes supporting the load, supporting what's going on here, going into this pulley system. And notice on the previous one that there was only 1, and we got a mechanical advantage of 1. So now let's go to a, again, more complicated pulley system. This one's going to have 4 pulleys. I got to make sure I get it drawn correctly because it's not necessarily intuitive to me. Okay, these 2 pulleys are going to be attached together and attached to a ceiling or something. You're going to pull down here, and this is going to just wrap around. We're going to wrap around this one, come up, wrap around that one, come up and attach to this pulley here, not to the whole system connected to the ceiling. Okay, so this is like a little hook or something. And then down here, we're going to connect the center of this pulley. No, don't do that. To the center of that pulley. Just like up here, this is to the center and that is to the center. Okay. And then off of that, this is where our load is. And you can see that this is complex now. We have a load, we have ourselves, we have 4 pulleys. But notice, we have 1, 2, 3, 4 ropes doing the supporting of the load here, which means following the trend we saw in the last 2 examples. 1 rope led to 1 ideal mechanical advantage of 1. 2 ropes led to ideal mechanical advantage of 2. And I forgot the 4 there. So in this case, the ideal mechanical advantage would be 4. Okay, so I realize that the examples from this unit do not cover everything in the unit. For example, we haven't done anything with efficiency. We haven't considered things like mechanical advantage, actual mechanical advantage, and those calculations. But I think this is going to set you up well for what you need to do.